Hello everyone, my name is Muhammad Iqbal. This is the final project of the Mechanism Sessional Lab. In this project, we have synthesized and simulated the windshield wiper mechanism with no quick return effect. Our team members are Muhammad Iqbal, Zaid Akhtar, Param, and Aakash Kumar. We have divided the presentation into four parts: synthesis process, MATLAB simulation, CAD design, and motion study. Now I'm going to explain the synthesis of the mechanism using overlay method. To synthesize a Viper mechanism, we use a simple 4-bar crank rocker model. We start by fixing the two ground pivots, then choose the input crank angle. For every input angle, we draw the crank and locate its endpoint. Then using a compass, we draw two circles, one centered on the crank end and one on the rocker pivot, with radii equal to coupler and rocker link lengths. The intersection of these two circles gives us the new position of the coupler-rocker joint. Connecting these points gives the instantaneous configuration of the mechanism. Repeating this for several angles allows us to visualize the motion and tune the link lengths by inspection. This graphical method automatically preserves constant link lengths and ensures correct motion transmission. With just a ruler and a compass, we can validate the sweep, check interferences, and decide final dimensions before moving to CAD or simulation.
Aakash Kumar, I am going to present MATLAB simulation and calculation behind it. This is the simulation. In this simulation, this is the crank, and here is the motor that rotates the cranks into 360 degree. Thus, the wiper T oscillates. Now, let's come to the code. Here is the parameter we defined for the wiper mechanism. We check the grasshopper condition to ensure that the crank will rotate 360-degree angles. Now, in section 2, closed form rocker calculation, in which we calculate for different orientation of crank the corresponding rocker position and orientation of wiper tip. The rocker angle theta 4 and the wiper orientation k are computed analytically using geometric relationship. The crank in points is given by x is equal to a cos theta and ay is equal to minus a sin theta. The coupler rocker distance is given by f is equal to square root d minus x square plus h minus ay square, and orientation is phi is given by tan inverse h minus ay upon d minus x. By applying the law of cosine, we can find cos of angle A. Thus, we can find the internal angle A. From here, we can find the theta 4, that is given by pi minus phi plus A, and the wiper angle K is given by pi plus delta minus theta 4 are obtained. These closed form of equation allow a smooth continuous motion of wipers.
My name is Param and I am going to be explaining the CAD design part of our project. We have done the design in SolidWorks, which is a computer aided design software. This is our model, which has been made in an assembly file. The assembly file is made by joining the subsequent components using different type of mates. For example, this joint here has been made using a coincident and concentric mate. This is the base body which has been fixed to the ground. The other joints are interconnected, ensuring proper motion with the movement of the crank. Now moving on how a subsequent part looks. This is made according to the dimensions which were required, ensuring proper alignment of all the parts. Moving on to the innovative aspect of our project. The initial design had a very low area of coverage and had a quick return mechanism. By editing the crank and coupler length, we are able to achieve a lot higher range of motion, also experiencing no quick return than before.
Hello everyone, my name is Mohammad Zaid Akhtar, and I'm here to discuss another great feature of the SolidWorks, that is motion study. So Motion study allows us to perform simulations and motion analysis. Using this tool, we have created a simulation already. Let's see. Okay, so how is it done, right? We can see the traces of the path and how is it done. We have used a motor that is attached here to perform the rotary motion, and then we can see like it is rotating in anti-clockwise direction with a constant 30 rpm. And then there's another great feature of the SolidWorks that we can perform motion analysis using, we can obtain graphs of various things. Like there are displacement, velocity, acceleration, there are forces that can be extracted. The momentum, energy, and power are also can be calculated. Let's see what can we get from the velocity and acceleration. So there are subcategory, the trace path, like we have already done here, and we can calculate a bunch of different things that we can see. So we have already made such two plots. So it is acceleration of the end effector versus time, and the angular velocity versus time. So what it actually shows. This plot shows that even though our motor runs at a constant RPM, the output link of the mechanism does not move uniformly. The waveform reveals how the linkage geometry naturally speeds up and slows down at specific angles. This is exactly what we want in a Viper mechanism: smooth sweeping in the middle and controlled slowdown near the reversal points. It proves that mechanism converts constant input motion into functionally useful non-linear output. The peak centers gives us clear insight into the efficiency of motor transmission, and it also tells us a lot about the dead center configurations. By understanding where velocity increases or drops, we can optimize linkage dimension for smoother operation. For the acceleration plot, this acceleration plot highlights the dynamic forces acting on the Viper linkage. The spikes represent the moment of highest mechanical load, especially during direction reversal. These are the regions where motor needs extra torque and the joint face maximum stress. This visualization helps us pinpoint exactly where the mechanism is most demanding. Setting these peaks allows us to begin design stronger components, reduce vibration, and ensure the system remains durable over long-term cycles. Essentially, this plot tells us how the mechanism feels the motion, not just how it moves, making it a powerful tool for engineering decisions. Thank you.